welcome to Plutus. And today we are covering entropy as a state function. So most of you already know that what is entropy. It is always defined as a degree of randomness or a measure of randomness. Today we'll try to explore how entropy was derived and why it was needed in the first place. So the thing is, if I start with entropy, you need to always remember that it was given. It was given given against the limitation of first law of thermodynamics. First law of thermodynamics, or you can also assume that it was that second law of it was given as first law of thermodynamics as limitation. The problem was the first law of thermodynamics always talks about that whatever the amount of energy change a system is having, it is always divided into two parts, that is the change of heat plus the change of work done. This was given by first law of thermodynamics. But the problem is the first law of thermodynamics do not talks about, let's say, if there's a vessel and it contains, let's say, some liquid particles and I'm providing heat to it. So as per first law of thermodynamics, whatever amount of energy I'm providing, this energy directly leads to the conversion of this liquid molecule to the vapors. But whenever we heat a liquid in a container, we always find that the area around the container gets warmed up. The container also gets warm. So that means whatever the amount of energy I'm providing, it is not being 100% utilized by the system. Some energy is lost for the side processes. For example, if I'm providing energy to it, first, the surface molecule will get the energy and they try to move on the surface. And in order to do so, they need to collide with one another and with the wall of container. So whatever the amount of heat I'm providing, it is being utilized or is being wasted in other side processes instead of direct conversion to the liquid form. So my entropy puts a limitation. It says that whenever I'm providing energy, as per first law of thermodynamics, there is some wastage of energy, although the total energy of the system remains constant. But there will always be a loss, and that loss is termed as entropy. And so, as per this, entropy is defined as degree of randomness, or since some amount of heat is being done here, you will find that some particles are moving on the upper side and as well as they are colliding with each other, which leads to the loss of heat. And we already know that heat gets converted to work done or work done gets converted to heat. So that means there will be some loss of work here. So entropy sometimes also defined as measure of unavailable work, unavailable work for system. That means the amount of heat that is not being utilized by the system for whatever the process we are looking for. Now, in order to explain it in a much better way, let's move to Carnot cycle, because it is the Carnot cycle that leads to the discovery of second law of thermodynamics. If second law of thermodynamics would have never existed, we never had second law of thermodynamics. So, as per Carnot cycle, we were provided that eta, which is the efficiency of any system, is given by 1 plus Q2 by Q1, or in terms of heat, is it provided by eta 1 minus T2 by T1, where T2 is lesser than T1 and Q1 is greater than Q2. So, as per Carnot cycle, the 100% heat that I'm providing to the system it is being utilized by the system completely and there is zero loss of heat. But we all know that in eta can never be 100%. It can never be achieved in real life. So let's suppose this Carnot cycle that I have, it is made of hundreds of individual Carnot cycle existing in the system. And this goes infinitely in all directions. Now, these infinite number of Carnot cycles, I can say from eta that 1 minus T2 by T1 will be equals to 1 plus Q2 by Q1. Separating, it will become minus of T2 by T1, which will be Q2 by Q1. Again separating the values, it will become Q2 by T2, Q1 minus by T1. And taking on the other side, this will become Q2 by T2 plus Q1 by T1, which equals to 0. So that means in a normal Carnot cycle, the total heat being supplied gets completely utilized. So there is no change. Now, since the thermodynamic cycle of the Carnot I'm talking about, it is divided infinitely. So if there are infinite number of steps, I can write Q1 T1, Q2 T2, and so on. They all will be equals to 0. So since it is a cyclic process, I can write this entire summation in the form of like this: Qi Ti, where I is equals to 1 equals to 0, but it's a cyclic process, so I can represent it by an integral in a reversible process by t, which is equals to 0. Now, a cyclic integral can only be 0 if it is a state function. If it is a state function, and since this is a state function, we named it as entropy. We named it as entropy, which is defined as rate of change of heat per unit temperature. This is your entropy. Now, this has now become your second law of thermodynamics, and it suggests that if I have this container, the amount of heat that I am providing to the molecules which are present at the bottom of it, these molecules transfer their energy to the molecule. Some of them gets formed to vapor, while some increase the temperature of the vessel and the nearby surrounding. If I need to give an example just how the second law of thermodynamics works in nature, you can assume that if there was never the need of entropy, let's assume there was never any entropy thing ever existed. So this means whatever the energy I'm providing, let's say I'm providing 100 degrees Celsius all at the same time. So as per first law of thermodynamics, all these molecules should directly get converted to vapor, and then the upper molecules will come down and then they turn into vapor. But instead, even if you provide 100 degrees Celsius at the same time, first what will happen? The water gets warm, then warmer, then hot, and then finally it achieves boiling point. That means some amount of energy was being utilized. Even after providing so much amount of heat, there was not 100% conversion of that heat into water vapors. So that's how we define that entropy is actually a state function, or the work done which cannot be utilized by the system. So I hope this would have cleared all your doubts regarding entropy and you have learned something new today. In case of any doubt, you can add it to the comment section and we'll get back to you. Thank you for joining us.